Last time we have discussed about diatomic case and the dispersion relations can be summarized something like this. This is I think pi over 2a something. And here the optical mode and acoustic mode, and at the k close to 0 we are going to have a straight line and non-dispersive system. Non-dispersive. And we can define each value, and particularly this point is corresponding to eta m plus 8 large M, square root of that. And this value is very important in a sense that when you draw the optical dispersion relations superimposed on this diagram, then it's the K of optical, the light, for example, is very big, so that the K is very small, so that if you draw the dispersion relations of the light in this diagram, then it should very close to this y-axis of this lattice atoms. So at this point, we are going to have same frequencies of the light and the lattice wave. In other words, if you shine the light on the solids, okay, and then at the frequencies of this light, this point is exactly the same to the frequencies of a lattice wave, and we call that the resonance. The resonance happens, and then we call this rest-Strahlen absorption. Suddenly, at the frequencies of light, at the specific frequencies, specific frequencies, the light can be observed into the solid. Okay, and then we call that the rest-Strahlen absorption. And this is very important to find the material characteristic, like bonding energies or things like that. For example, NaCl case, okay, typical ionic materials. This frequency is going to be called K close to 0, and we have 2 points of 2 omega values at K close to 0, which this one is going to be O minus, and this is going to be O plus, right? So the frequency is measured is going to be 3.1 times 10 to the 13 hertz, and the radius of sodium is 0.95 angstrom, and radius of chlorine is going to be 1.81 angstrom. So 1 over m plus 1 over small m is going to be 4.167 times 10 to 22 per gram. And the lattice parameter is 2.76 angstrom. So, rest straddle and absorption frequencies. This frequency is going to be rest straddle and absorption frequencies. That rest straddle and absorption frequency should be square of this. We are talking about this point, okay? The square of this is going to be 2f over 2.76 times 10 to the 8 minus 8 centimeter times 4.167 times 10 to the 22 per gram. All right? So we can get the values, the bonding energies of sodium and chlorine ions in this ionic material is going to be 3.18 times 10 to the minus 4 dyne. All right? So by shining a light to sodium, the NaCl solid, okay, and then you measure the absorption peak, then you can get the rest straddle and absorption frequencies, and that frequency should be corresponding to these values. So you can find the binding energies between sodium and chlorine. You can get these values by a Coulombic law. You can get the binding energies between two ions, which is going to be d square q square, and then that is 1 square 4.8 times 10 to the minus 10 square over 2.76 times 10 to the minus 8 square. And this is going to be 3.02 times 10 to the minus 4 dyne. These two values are very close, right? So this rest straddle and absorption, especially very effective for the ionic materials, is a good method to get the binding energies between the atoms. Okay, what happens if we have more than 2 atoms in a lattice? Then that dispersion relation is going to be, we are going to have 3 acoustic mode. 3 acoustic mode. And then we're going to have three times n minus 1 optical mode. This is going to be multi-atoms case. We're going to have dispersion relations, something like that. All right. Finally, let me give you some numbers so that you can get some pictures what the energies we are talking about. Okay. Phonon energies, phonon energy for sound, that's a longitudinal wave at k equal to 0, right? K is about 0. And that is h bar omega, and then the typical numbers corresponding to this is 0.55 times 10 to minus 27 or sec times 1 times 10 to the 12 sec minus 1 and 2 pi. 2 pi. And you end up with 63 times 10 to minus 16 or which is 5 milli electron volts. Okay, and phonon energies for optical mode. At long wavelength. That is maximum energies the lattice can have. We are talking about at this point, right? The maximum energy, the energy is going to be just h bar omega. This is a constant, so it's a function of frequencies only. So at this point, this is the energy of the lattice can have, maximum energy the lattice can have, right? So this is the maximum phonon energy. And then if you calculate that, again, energy is h bar omega. So this is going to be 6.626 times 10 to the minus 27 erg sec times 5 times 10 to the 12 hertz and 2 pi. Then you end up with 3.313 times 10 to the minus 14 erg, which is going to be 330 to 50 milli electron volts. So the phonon energy we are talking about, it's around about, the maximum is millivolts, 10 millivolts, the order of 10 millivolts, and the minimum energy is just 5 to 6 milli electron volts. That is just the figures that we can have for the energies we are talking about. All right? Where's my pen? I just dropped my pen. Okay, the next chapter is going to be light wave. After this light wave, we are going to talk about the matter wave. Okay, we are going to talk about the 3 wave systems. We start out with a string under tension, and we have found that in this case we are going to have a standing wave, and then we can see why there's a difference between the oscillator and particle in a box. in a box. Okay? In oscillator case, the energy quantized equally. Delta E is h bar omega. But in a particle in a box case, the ground state, and as you go higher and higher, the energy gap becomes delta E proportional to the n square, the quantization number. Okay? So we can understand why we don't have the X-rays out of the high temperature furnace, but we do have X-rays in the case of copper metals under the high electric field, right? So that's a very simple. We use the F equal to ma to deduce the wave equation for this, but we end up with very astonishing results, okay? And we're going to apply this thing, this wave equations to three systems. The first one is the lattice wave that we have discussed in the last lecture. And the second one, which is going to be discussed today, that is the light wave. And the next one is going to be matter wave. Matter wave is just the matter itself, like electrons. Probably you may figure that electrons look like a ball, okay? But we do want to regard this as a wave. It's just a weird thing, right? We want to regard this ball as some kind of wave where the position and the momentum is not defined. It should be in the space, something like that. So this is not an easy task that we might have. And the light wave is different from the lattice wave in a sense that it doesn't have a mass. So we should have applied a different approach to get this light wave. Somehow we do want to have a partial differential equations which is going to look like round T m over round m psi should be equal to round x n round n psi. Right? We should have this kind of equations to represent the thing into the wave. So in the lattice case, it was easy. We do have mass, okay? And then we know the force in the lattice. But how can you get the wave equations for the light, which doesn't have any mass, that doesn't have any forces between the medium that we are talking about, the light. So in order to solve that problem, what we are going to do is we are going to use Maxwell equations. Maxwell equations. What is the Maxwell equations? Maxwell equation is just is nothing but a mathematical expression for the observations, the physical observations. Like the first Maxwell equations, this Maxwell equations has been covered in your high school days, right? So let me introduce the Maxwell equations and how can we use the Maxwell equation to deduce the wave equations for the light. All right. Now we have 4 Maxwell equations, and again I should emphasize that Maxwell equation is nothing but a mathematical representation of what we ordinarily observe, physically observe. For example, the first Maxwell equations is related to the electrical charge. Electrical charge can be isolated. And for that mathematical formula to represent this phenomenon, physical phenomenon, is the divergence of electric field is going to be the charge density. This is the mathematical formula which can be interpreted as the electrical charge can be isolated, the charge density there. That is the Maxwell's first equation. What is the second equation? Second equation is nothing but no magnetic pole can be isolated. So differently from the electrical charge, okay? The magnetic pole cannot be isolated. The N and S pole cannot be isolated. No matter how small you just cut the magnetic materials, the small piece of the magnetic materials always have NS. The N and S cannot be isolated. The electrical charge, the plus charge and minus charge can be isolated, right? So how can you tell this phenomenon into mathematical form? That is, the evidence of a magnetic field is 0. Simply, no magnetic pole can be isolated means the divergence of is a closed system. Divergence of a magnetic field has to be 0. Now, what is the third equation? Change in magnetic field. Change in magnetic field induce electric field. That is the third Maxwell equation, and the mathematical representation of this phenomenon is